Welcome back to our lesson on probability. Now, I'm sure that you are enjoying the idea of being able to predict the future using mathematics. Probability helps you understand what are the chances of certain events taking place. And it doesn't just have to be one event. It can be more than one event. Now, in this lesson, we're exploring the idea of two different events taking place. And so let's get into the idea of the two events. And what are the nature of these two events? Are they related? Do they have some common elements in them, or don't they? Well, that's exactly what we want to explore, because maybe the rules are different for different types of events that are taking place. So let's have a look. We're dealing with two events, and we recognize that these two events can either be thought about as both of them together, in which case the winner might be found if they have an outcome in one of them or the other. So union is always referred to in terms of the word or. Whereas what we want to look at is the idea of intersection. We've already seen that in terms of intersection, some two events have no intersection. And we're going to explain what this word then means. The idea of something being mutually exclusive. So right from the beginning, let's talk about intersection of two sets. So if we have an intersection, well, that means that they overlap in some way. It also means that there's an element must be in set A and in set B if it's part of the intersection. It just can't be in A on its own. It can't be B on its own. It has to be in A and B if it belongs to the intersection. And so that's a very important thing, because the intersection is smaller than the union. Please remember that. We kind of get that mixed up in our heads, and we can make a mistake by not recognizing that union means the bigger thing, and we're saying that it is an A or B, where the criteria for intersection means it must be an A and B. So it's smaller, it's common. But of course, there's a situation where the intersection could have no common elements, like the examples that we were dealing with in the previous segment. So let's just have a look in our definitions, how we define intersection in a little bit more detail. So the intersection is a new set that contains all of the elements that are in both sets. So it's not just in one, but they must be in both. You can't be in the intersection if you're not in both. We write the idea of intersection not as a U, but an upside down U. So it's that funny symbol. If we draw it like that. And remember, intersection is referenced as and. Now, how can we remember this? Well, a friend of mine was telling me one of the ways that he remembers this, if you have two roads that are running at 90 degrees to each other, then the intersection is the part of the road that belongs to both of them. So if you've got a road running from north to south, and you've got a road running from east to west, that part that belongs to both roads, that's the intersection. And it's smaller than the union of those roads. The union of those roads would be either to be on road that is running from east to west, or on the road that is running from north to south. Okay, so please be very clear about your language here, and build up a mental picture so that you are very clear about what intersection and union mean. Because lots of formula and examples and exercises will relate to your understanding of these two important words. Let's move on. So we're going back to our example of our 10 letters, And remember, that's the first 10 letters of the alphabet. And we recognize that is in the sample space. We recognize X has got 3 letters in it, and Y has got 3 letters in it. There is no common element. There is no intersection between X and Y. We would have to say that the number of elements in the intersection of X and Y is going to be 0. Okay? The number of elements in the intersection is 0. There is no overlap in this space. And so, because there is no overlap, there's no element, there's no crossing over. It's like 2 roads that don't ever meet. They could be running parallel to each other. They're going to be nothing in common with each other. And so we say that the intersection is a null set. It's an empty set. Okay, very important for that. They are separate. And this is where we want to get to in defining a very important idea of 2 sets. And it's the idea of something being mutually exclusive. Wow, that's a difficult word or phrase to get out. Mutually means something in common. Exclusive means that they are set apart. So they are different but set apart. So the idea here is that there is no intersection. So when we define mutually exclusive, it simply means events that cannot occur at the same time. Very, very important. Even at a high level on studies on probability, you would be asked to identify, is an event mutually exclusive or not? And it's not that difficult to recognize. If these events do not have anything in common, then they are mutually exclusive. So they can't take place at the same time. So for example, you can't put a sock on your foot at the same time as putting a shoe on the foot on that same foot. It can't happen at the same time. You can't take a dice and roll it and get a 6 and a 3 at the same time. Rolling a 6 and rolling a 3 would be mutually exclusive events. They cannot take place for one die at the same time. So please make sure you've got this very clear in your head. Now, we often need to test if something is mutually exclusive. And so we're going to do a little exercise or activity that helps us understand what that idea of, for mutually exclusive, the union of 2 sets is. So have a look at the data, and I want to remind you that they're asking you, or look at the data first of all. We're saying that the probability of R is going to be 0,4. The probability of T is going to be 0,2. And they ask us, in terms of these 2 sets that are mutually exclusive, they're written as mutually exclusive events, they're representing events, they're sets, Venn diagrams, and we want to be able to say, what is the probability of those 2 together? If it's mutually exclusive, remember we said the probability, when it's mutually exclusive, we're going to recognize it's the probability of R union T, and we're going to say then that's equal to the probability of R plus the probability of T. Now, in this case, we recognize the probability of R is 0,4, and the probability of T is 0,2. We can add those 2 together to get us a probability of 0,6. Now, please remember that that law or that identity applies for mutually exclusive events. When there is no intersection, the probability of R or T taking place is 0,6. Very good. Let's move on and have a look at another example of the same application. And here we're going to ask the question, does this identity hold true for events or sets that are not mutually exclusive? I want you to think about that. Do you really think that that will work or not? I want you to reflect on it. And I'm not going to answer it in this lesson, but you'll have to wait for our next lesson to do that. But in the meantime, let's have a look at another problem. And this problem says to us the following things. The following sets, are the following sets mutually exclusive? We know if they are mutually exclusive, then we can take the probability of each of them, add them to each other, and we would find the probability of the union. So let's make sure that we've got this clear. So for mutually exclusive sets, we can say, let's take the probability of M happening plus the probability of N happening, and we can say that's 0,7 plus 0,2. And look what we get. We get an answer of 0,9. And can you see that this is not equal to the probability of M or N? So it breaks apart. It doesn't look like it's following the identity. Well, you might scratch your head and say, have I made a mistake? No, you haven't made a mistake. The reason that these two do not add up, they are not equal, is because M and N are not mutually exclusive. And there we go. Guys, if you can remember this one fact, that what mutually exclusive means and how to determine it, I promise you, you will win at your probability investigations. We're going to have a look at what happens when there are elements in the intersection. But that we will leave for another time, and we'll think about whether that same identity can be applied. But before we go, let's have a look at a brief summary. So, what have we done so far in our investigations of probability? Yes, we've looked at Venn diagrams. We've recognized we can have a sample space with all the elements, and we can recognize that we can have a sample space with elements that belong to different sets. These sets don't have a common element in them, and we would recognize that these ones, as I've drawn them, are mutually exclusive. There is nothing in the intersection. On the other hand, I could have two sets, and I'm not going to call them the same. I'm going to call them P and Q, and in this case, let me just make this one a bit bigger. That one is Q, and you recognize there's an intersection. There are common elements. These are not mutually exclusive. So, recognize now, when we talk about union and intersection, we have a very clear definition of those two events. Make sure that you've got it. Union means we're always going to say the objects or the elements must be in the one or the other. So when we are calculating union, we're looking in either of them. Where we're looking at intersection, we're saying this is the smaller one, the intersection is going to be the and. Okay, so it has to be in both, common to both. It's in the intersection. Very good. Now remember, when we calculate the probability of the union, we have said the probability of the union is going to be the probability of A union B is equal to the probability of A plus the probability of B if the sets do not have an intersection. That is only true if we are dealing with mutually exclusive events. So, guys, I hope this is very clear. I know we've gone through a lot of different new terms and different terminologies, but please revise this and make sure you can apply your identities, your probability identities, for calculating probabilities when you've got two sets that you're looking for the union and they are mutually exclusive. That's been the main focus of what we're dealing, and I'm going to wish you all the best as you continue investigating more about probability.